So if you ever watch a marathon, you'll notice the runners are wearing these incredibly light, highly specialized shoes.
Oh, yeah. Engineered down to the gram.
Exactly. They're built for just one specific physical task, right? Like sustained, efficient forward motion over a long, flat distance.
Right.
But now, imagine if, like halfway through that 26-mile race, the course just suddenly alters. The runner rounds a corner and is facing a vertical rock wall.
Wow, okay.
And right after that, they have to navigate a delicate, swaying tightrope. Those perfectly engineered marathon shoes instantly become this massive liability.
Because the foam is too thick to feel the tightrope.
Yes, and there's zero grip for the rock wall. You wouldn't just need different shoes to survive that course. I mean, you'd almost need a completely different physical physiology to handle those transitions safely.
Well, you're asking a system that was fundamentally optimized for one static identity to suddenly master something completely different.
Right.
From an engineering standpoint, that's just an impossible demand for a static piece of hardware. A marathon runner's biomechanics are actively fighting against the requirements of a rock climber.
And that tension, that exact tension between what a machine is built to do and what a chaotic environment demands of it, that's what we are unpacking today.
I'm really looking forward to this one.
So welcome to the deep dive. We are looking at a truly fascinating pre-engineering concept paper today. It's titled Phase Adaptive Compact Drone.
By Lev Nemotin, PhD.
Yes, exactly. And for those of you who don't know him, Nemotin is a deeply interdisciplinary thinker. He's actually the creator of the Uncompressed Thinking channel.
Which is a fantastic resource, by the way.
It really is. It's this brilliant space where he explores physics, systems design, and unconventional engineering through, like, incredibly clear mechanism-based reasoning.
Yeah, he really focuses on the actual mechanics of how things work.
And that focus is going to be our guiding light today. But to set the baseline here, Nemotin's concept actually grows out of his earlier work, right?
Right, yeah. It comes directly from his work for the Office of Naval Research. He was developing underwater linear stroke electric engines.
Oh, interesting. So underwater.
Yeah, but the core problem he faced in fluid dynamics underwater is the exact same problem engineers face in the air.
Which is what?
Well, how does a single unmanned platform operate across widely different, rapidly changing dynamic conditions without just losing all of its mechanical efficiency?
Okay, let's unpack this a bit. Because if you're listening to this and picturing someone in their garage just soldering 3 different engines to a plastic drone frame, we need to reset the framing.
Yeah, definitely. This is not a technical step-by-step manufacturing manual today.
No, it's a conceptual exploration. Nemotin is asking us to completely rethink movement and propulsion.
Right. Instead of looking at propulsion as a static piece of hardware, he's framing it as a time-dependent system.
Like those marathon shoes that can never change their shape.
Exactly. He is proposing a drone that literally changes its entire physical identity on the fly. It orchestrates different energy states depending on what the immediate seconds demand.
It's fascinating here is that the traditional approach to surviving complex environments has always been a search for the magic bullet.
Oh, absolutely. Like one perfect, highly compromised engine that tries to just do everything.
Right, but Nemotin realized that the answer isn't a single engine.
It's acknowledging the physical distinctness of different flight needs. And he addresses them through deliberate regime specialization.
Meaning orchestrating 3 fundamentally different engines on one compact airframe.
That's the idea, yeah.
Okay, wait, hold on. You're putting 3 different propulsion systems on one tiny drone frame.
I know, it sounds crazy.
I mean, I'm picturing a flying Prius, essentially. Aren't we just slapping 3 engines together to get a bit more capability?
I get why you'd think that.
Because aerodynamically, they want completely different shapes. Isn't this just going to be a heavy, cluttered mess, like a jack-of-all-trades that's master of absolutely none?
That is the immediate intuitive assumption. But the paper explicitly warns against that trap.
Oh, it does?
Yeah. If this were just an additive hybrid, like where you run a combustion engine to charge a battery to spin a propeller,
Like a Prius?
exactly like a Prius,
Yeah.
that would be a massive failure of design here. It would succumb to the weight penalty immediately.
Okay, so how is this different?
What Nemotin's describing is an energy hierarchy based on a concept of orthogonality.
Orthogonality. Meaning they operate at right angles to each other.
Conceptually, yes. They don't compete because they operate on entirely different physical axes.
Okay, let's break down those axes, because the paper categorizes them into 3 distinct domains.
Right.
First, you have the electric regime, which Nemotin calls the domain of control.
Right, the domain of control. Its defining strengths are immediate torque, fine modulation, and reversibility.
Think about the mechanics of an electric motor versus a combustion engine.
Oh yeah, it's night and day. When an onboard computer tells an electric motor to spin faster, it happens in milliseconds.
Because it's just a change in electromagnetic current.
Exactly. There is no fluid to pump, no explosion to wait for.
So that's why electric propulsion doesn't define where the drone goes.
Right, it defines how accurately it inhabits a specific local space.
It acts as the micromuscles of the aircraft.
I like that. Yes, micromuscles. It handles the tiny fraction of a second adjustments needed to hover in a crosswind or navigate a tight corridor.
So the electric layer is your scalpel.
Beautifully put.
Then we move to the second layer, the combustion regime.
Yes, the domain of persistence.
This is the structural backbone of the drone, right? Because combustion provides incredibly high energy density.
Right, a tank of liquid fuel contains vastly more usable energy by weight than current lithium-ion batteries.
Right.
And because it has that energy density, the combustion engine provides stable, sustained thrust.
So in this regime, the drone becomes a traveler.
Exactly. The combustion engine takes on the macro workload.
It's the deep, sustained muscle movement that pushes the airframe across miles of distance without just instantly exhausting the batteries.
Right. And then we get to the third layer, which is where this concept gets truly radical.
A jet regime.
Yes, the domain of surge.
And this is not about precision, and it's definitely not about persistence.
No, not at all. It is a transformational burst.
When the jet turbine activates, the drone briefly becomes almost projectile-like, doesn't it?
Yeah, it provides a sudden, massive spike in acceleration for steep climbs or rapid dashes.
Stuff that the electric and combustion systems physically cannot achieve no matter how hard you push them.
Exactly. So we have three completely distinct mechanical philosophies sharing the same chassis.
The scalpel, the workhorse, and the rocket.
Perfectly summarized.
But here's my issue with that. If I have 3 different engines firing, aerodynamically, they're going to tear the drone apart.
Oh, absolutely.
Like a jet thrusting forward while electric rotors are trying to maintain a delicate hover. That is a recipe for a spin-out.
It would be a total disaster.
So how does the onboard computer decide who is actually driving the machine at any given moment?
Well, that brings us to the orchestration layer, which Nemotin maps out beautifully as the phase map of flight.
Right, the phase map.
The governing rule of this system is incredibly strict. At every single moment of flight, one regime leads, one may assist, and one must remain absolutely silent.
Oh, so they never all fire at once.
No. If all three demand equal voice, you don't get an adaptive drone. You get an aerodynamic conflict that results in a crash.
Okay, let's walk through this phase map then, starting at the beginning.
Sure.
Phases 0 and 1 represent takeoff and initial climb.
Right.
And the rule here is that the drone starts purely electric. Why is that?
Well, if we think about the physics of taking off, especially a vertical or short takeoff, the air near the ground is incredibly chaotic.
Oh, because of ground effect.
Yes. The air bouncing off the pavement creates unpredictable turbulence. So you need the millisecond reaction times of the electric motors to keep the airframe level.
Right, a jet engine blasting off the pavement would be entirely uncontrollable.
And a combustion engine just spools up way too slowly to catch a sudden roll.
So it begins with control, not force.
Exactly.
Yeah.
The drone has to establish a stable relationship with the air before it does anything else.
But once it clears that chaotic ground layer and transitions into sustained flight.
Which the paper calls phases 2 through 4.
Right, we see the first major mechanical handoff. The combustion engine fires up and becomes the dominant regime.
Right.
And the electric motors don't just turn off, right? They change their job description.
Exactly. They step back. They stop providing the primary lifting or forward thrust.
And they transition into being purely micro-stabilizers.
Yes, they just iron out the aerodynamic wrinkles while the combustion engine does the heavy lifting.
Literally pushing the mass through the sky.
There is a deeply philosophical line in the paper here, actually.
Oh, what is it?
It says the drone must become ordinary before it can become extraordinary.
Wow, I love that. It earns its complexity by proving it can be a stable traveler.
Yeah, it proves it can just do the boring, efficient work of flying straight and level.
But let's say the environment suddenly changes. The drone encounters a hostile threat, or it needs to rapidly scale a building.
Then we hit phase 6, the surge.
The jet activates.
Yes, and for a few seconds, the drone time shares its own physical body.
It completely abandons its identity as a stable traveler and transforms into a high-energy projectile.
And the physics of that moment are violent. The jet provides a localized, highly managed explosion of kinetic energy.
The G-forces spike, the thermal output skyrockets.
Yeah, the drone is basically riding a controlled explosion to escape a threat.
But entering that state isn't even the hardest part, is it?
No, not at all. Phase 7, the restabilization, is arguably the most critical engineering challenge of the entire phase map.
Because when that jet shuts down, you suddenly lose a massive amount of forward thrust.
Right, and the aerodynamic pressure on the airframe completely shifts.
It's a massive shock to the system.
Exactly. The drone has to bleed off that excess kinetic energy and smoothly hand authority back to the combustion and electric regimes.
Before it just stalls and falls out of the sky.
Right. Because if we look at this through the lens of systems design, a system that can enter a burst state but cannot cleanly and safely exit it isn't truly adaptive.
No, what does he call it? It's just excitable.
Yes, excitable.
Excitable. That's such a perfect description of a system that just throws a tantrum and crashes.
Right. It has to be able to calm down and become the traveler again.
So the entire temporal sequence goes control to sustain to transform to stabilize and eventually back to control for landing.
That is the time structure of the propulsion.
But let's get back to the physical reality of actually building this thing.
Okay.
A jet is essentially a contained inferno. You are putting a fire-breathing metal tube inches away from sensitive lithium-ion batteries.
And delicate flight controllers, yes.
Plus, you have the physical mass of a fuel tank, a battery bank, and 3 different motors.
Yeah, it's a lot.
Doesn't the sheer weight of this system just crush its own efficiency?
Well, that is the exact engineering tension Emotin wrestles with in his conflict map.
Because the thermal, mass, and aerodynamic conflicts are severe.
Very severe. And the solution he proposes is found in what he calls the minimal viable architecture.
Meaning you cannot put 3 full-sized, fully optimized engines on one drone.
Exactly.
Okay.
If you try to give it the best jet, the best combustion engine, and the biggest batteries, the weight just balloons.
And the heat destroys the electronics.
Right. So the solution requires a strict philosophy of biased compromise.
Let's put an analogy to that biased compromise. Think about, like, an elite triathlete.
Okay, I like where this is going.
A triathlete is never going to beat an Olympic sprinter in a 100-meter dash on the track.
Definitely not.
And they are also never going to beat a pure Tour de France cyclist up a mountain.
Right.
They carry a very specific biased compromise in their physiology. They have enough upper body muscle to survive the swim, but they are lean enough to run a marathon.
And enough leg power to bike.
Exactly. They are acceptable in all 3 regimes, but perfectly optimized for absolutely none of them.
And that physical restraint is the secret to the drone's architecture. The combustion engine is sized only for stable cruise, not for aggressive, high-angle maneuvers.
And the electric battery is sized only for short bursts of precision and stabilization.
Right, not for a 30-minute flight. And the jet, well, the jet is the most seductive and dangerous part of the entire design.
Because it must be kept incredibly small.
It is explicitly designed as a timed event generator, not a primary mode of travel.
Because if you make the jet too big, you fall into a trap. The paper calls jet dominance drift, right?
Yes, jet dominance drift.
You start realizing the jet is really fast, so you use it more. But to use it more, you need bigger air intakes.
And then you need heavy thermal shielding to protect the batteries from the sustained heat.
And suddenly, you've redesigned the whole airframe to support the jet.
And the surge layer has become a lifestyle rather than a rare event.
It stops being an adaptive trimodal drone and just becomes a terribly inefficient jet aircraft carrying a bunch of dead weight.
Exactly. And that ties directly into the thermal logic of the system, which is just brilliant in its simplicity.
Because heat must be managed as a temporal event, not a permanent climate.
Right. Let's explain how the drone actually survives the jet burst without, heavy liquid cooling systems.
It relies on a concept similar to thermal soaking.
Yes. If you pass your hand quickly through a candle flame, that's an event. You don't get burned.
The heat doesn't have time to penetrate your skin.
But if you hold your hand there, creating a
What a
cloud.
blister.
Exactly. So the internal components treat the jet heat like a passing hand.
The burst is so incredibly brief, maybe 4 or 5 seconds, that the ambient heat doesn't have time to penetrate the insulation.
And it doesn't cook the lithium batteries. Precisely. By the time the heat begins to soak into the surrounding chassis, the jet is already shut down.
And the drone is using the massive airflow of its forward momentum during the cruise phase to passively cool the system down.
Right. If the mission parameters require you to install massive, heavy active cooling systems just to survive the jet phase, the concept has already failed.
The restraint was lost.
Exactly.
So it really is an aerodynamic tightrope walk. You have to maintain this strict hierarchy.
Yes, combustion is the backbone.
Electric is the nervous system.
And the jet is just a momentary adrenaline spike.
Which brings up a very practical question.
Okay.
If it is this incredibly difficult to balance these physical conflicts, and you have to accept all these compromises, where is this actually useful?
That's the million-dollar question.
Like, why go through all this trouble instead of just using a normal drone?
Well, the author is intellectually honest about the limitations. The conclusion of the paper is deliberately restrained.
Meaning this trimodal drone is not broadly advantageous.
No, you would never use this architecture for a simple package delivery route across a city.
Or a basic wedding photography mission.
Right. It is selectively transformative within a very narrow, highly specific class of missions.
The paper outlines several of these mission windows, and Type I really paints a vivid picture of why this exists.
Yeah, Type I is defined as distance, then precision, then rapid exit.
Imagine you need a drone to inspect a highly sensitive asset far offshore.
Let's say an oil rig in contested waters.
Right. First, it has to travel 50 miles over the ocean. A pure electric drone can't make it.
And a pure jet would just burn all its fuel.
So it uses the efficient combustion phase.
Then it arrives at the rig. It needs to enter a highly constrained, delicate environment.
Navigating between steel pipes and sensors to inspect a valve closely.
Without crashing into it or blowing things around with massive exhaust.
So the combustion engine shuts down.
And it relies on the electric phase, giving it that scalpel-like, millimeter-perfect control.
But then the environment suddenly turns hostile. Maybe a severe squall line hits, or it's detected in a restricted area.
And it needs to evacuate immediately.
It needs to clear the structure faster than the combustion engine can spool up.
Boom. The jet activates.
It surges out of the danger zone instantly, putting distance between itself and the threat before restabilizing for the flight home.
And in that specific scenario, we see the true comparative advantage of Namon's concept.
It breaks what engineers call sequential trade-offs.
Exactly. In a simpler dual-mode drone, say just combustion and electric.
Optimizing for that long ocean cruise means you severely degrade your ability to sprint away at the end.
Or if you build a combustion jet drone, you can travel and you can sprint.
But you completely lack that delicate electric precision when you're actually trying to thread the needle during the inspection.
Right. The trimodal system allows each phase of the mission to be executed near its local optimum without ruining the other phases.
You aren't dragging the heavy compromises of the cruise phase into the frantic reality of the escape phase.
Another crucial mechanical advantage here is that this architecture completely decouples control from energy.
Oh, right. Because in a lot of traditional aviation systems, to get more control authority, like to turn sharper or fight a wind gust.
You have to apply more thrust.
But with the electric layer operating independently, you have high precision and high aerodynamic authority, even in low-thrust, delicate hovering states.
It separates the variables. You are spending your time economically with the combustion engine.
And you're spending your power strategically with the jet. So what does this all mean? Like, why does an exploration of drone propulsion matter to anyone who isn't an aerospace engineer?
That's a great point to bring up.
Because I think this paper is just a profound masterclass in systems thinking.
Absolutely.
So often in our own lives, in business structures or in software development, we try to build a single tool or a single process that is supposed to be perfectly optimized for every possible situation.
We want the marathon shoe that also somehow climbs rock walls.
And what invariably happens, we end up with bloated, heavily compromised, convoluted systems.
Systems that are mediocre at everything.
And they violently fail the moment the environment throws a true curveball.
It's the difference between trying to be everything all at once, which always leads to clutter en masse,
and having the discipline to be exactly the right thing at exactly the right time.
Namotan is teaching us that sometimes you don't need a tool that is great on average.
You need a system that has the deep restraint to adapt its entire physical identity at critical moments.
Without ever losing its core backbone.
Right. We've moved from the old way of just cataloging static hardware, counting engines, and comparing battery sizes,
to this elegant, time-dependent orchestration of energy.
We've seen how precision, persistence, and surge can actually coexist in one physical body.
but only if they are bound by strict physical compromise and an unforgiving phase map.
Exactly.
This whole exploration raises a really profound question if we look beyond just the rotors and the turbines.
Oh, wow. What's that?
We've been analyzing how this machine intelligently switches physical regimes to survive chaotic environments, right? But if you zoom out, this blueprint perfectly mirrors advanced biology.
Wait, really? How so?
Think about the human body's adrenaline response. You are walking down the street, that's your efficient baseline combustion cruise.
Okay, tracking.
Suddenly, a car swerves toward the sidewalk. You don't consciously decide to run faster.
Your autonomic nervous system dumps a massive amount of adrenaline into your bloodstream.
Exactly. Your heart rate spikes, your blood vessels constrict. For a few seconds, your body undergoes a massive metabolic shift to survive an extreme event.
Oh, wow. It's your own personal jet surge layer.
Precisely. And then crucially, you have to stabilize, dump that chemical heat, and return to your baseline walk.
That is fascinating.
So as robotics and artificial intelligence evolve with this kind of strict hardware-level regime-switching architecture.
Are we witnessing the mechanical equivalent of an autonomic nervous system?
Exactly. Are we looking at a near future where a machine doesn't just execute a pre-programmed mathematical flight plan,
but literally undergoes a physical fight or flight metabolic shift based on environmental stress?
It's something to think about.
A mechanical autonomic nervous system. That is a wild thought to leave on.
I thought you'd like that.
Thank you for joining us on this deep dive into the phase-adaptive drone. Stay insanely curious, keep looking at the hidden systems around you, and we'll catch you next time.